Hey there, so this video should help you to debrief and understand the activities at the water stations or the water lab stations. Let's first talk about hydrogen bonds really quickly. So hydrogen bonds, as you know, occur in between water molecules because of the positive side and the negative side. Each water molecule is attracted to one another. And we do call it a hydrogen bond. Right here we say that this is a hydrogen bond. However, please understand that this is, it's not a bond, it's a weak attractive force. So it's more like magnets that come together and can pull apart. They can be broken, and when they're broken, when the hydrogen bond comes apart or is broken, no chemical change has happened. So this water molecule is still a water molecule, and this water molecule is still a water molecule. So usually when a chemical bond, like a polar bond, polar covalent or ionic bond, when those are broken, a chemical change has happened. You have a different substance, and this is not the case here. So please keep that in mind. Our first station, water is glue. The slide on the top and the slide on the bottom were held together by the forces caused by adhesion and cohesion. So cohesion, these water molecules were sticking together, so there was some attached to this slide and some attached to that side, and they were attracted to one another. And there were also, those water molecules with positive and negative sides were also attracted to the charged glass. Remember that glass usually has a charge, or glass does have a charge, and sometimes it's positive, sometimes it's negative. For the sake of this lab, we just said that it was negative. So here, the water molecules were attracted to the negative charge of the glass. And so that held the two slides together. The paperclip float. The properties here were cohesion and surface tension. So surface tension is a product of cohesion. So you can't really have one without the other. They're related. And we understand by this point that there's going to be this attractive force in between water molecules. However, there's going to be a difference at the top here. So the water molecules down here underwater, they're being pulled on every direction by other water molecules. So they're being pushed and pulled by other water molecules because of the weak attractive forces between each water molecule. But up here, if this is the surface, there is no there are no water molecules here pushing or pulling on these surface molecules. And so because of that, they can align themselves a little bit more closely together. Where these are being pulled apart, this space here is going to increase. And because there's less things pulling on these water molecules, they're going to align more closely, and therefore they're going to have a stronger cohesive force. So like if you were to take a magnet and it's very far apart, it's easy to pull that magnet away. But if you put those two magnets very close together, then it's more difficult to pull it away, because when those charges get closer together, it's harder to pull them apart. And so that's why you have that thin layer, or that skin, on top of the water. And that's what allowed the paperclip to float. And then we put some soap in the, here, let me move. We put some soap into the water. And we said that soap is amphipathic, amphi meaning both. So if we have an amphibian, that's an organism that lives both on water and land, like a frog. So here, if it's amphipathic, both, this water molecule, the soap molecules, or the detergent molecules, are going to be both polar and nonpolar. So here we have the polar heads, and we have nonpolar tails. And so it should make sense that these polar heads, this polar side of the molecule, is attracted to the water because it's charged. And so the charges are attracted. So it pulls it right in. However, these nonpolar tails are going to get squished right out because they aren't charged. And so they're going to stick right up out of the water because they're nonpolar. And now we have these amphipathic molecules sticking up out of the water, breaking up the surface tension, not allowing the that skin to form and making the paperclip drop. So the amphipathic nature of detergent is what allows the surface tension to be broken. So why does detergent or surfactant, detergent is a type of surfactant, why do we use it to clean? Well, it's because of this amphipathic nature. We'll put soap on our hands, so we'll put this amphipathic molecule on our hands, and what happens is the nonpolar sides are going to be attracted to the nonpolar grease or oils on our hands. That's got dirt, so dirt and oil on our hands. The nonpolar side is going to be attracted to that, while the polar side is going to be attracted to water. And in water, they're going to form these micelles. These micelles are like a little circle of amphipathic molecules. And when we get all of these little micelles filled with dirt and oil, we'll put our hands under water, or we'll rinse off our clothes after we washed them, and it washes away all of the dirt and oil. And so this is why we use detergent to clean our hands, to clean our clothes, etc. Now let's look at the drops on a penny. The surface tension, you can see the surface tension if you got like 20 drops of water. Some people got 40 drops of water, and everybody did a great job. And when you had all those drops of water on the penny, you could see the cohesion. So the water molecules stayed right on that penny, and there was that surface tension that held the water, so much more water than you probably expected. And it almost like hung over the edges, defying gravity. And that's because the cohesive force was greater than the force of gravity pulling down. And then we put alcohol on the penny, and you probably got fewer drops on the back of that penny. And this is because while alcohol is still a polar molecule, it's just less polar. So alcohol has a polar side here, and then it has these nonpolar, really short nonpolar tails that just get in the way of the hydrogen bonds. So while there's still an attractive force, it's just less because it's more crowded. So there's more things getting in the way, and so those magnets can't get as close together. And so therefore the cohesive force is just a little bit less. All right, let me move myself here. Drops on glass and plastic, or drops on glass and wax paper. Here we put drops of water onto wax paper, and you can see it beaded up. And this is because the water was not going to interact with the wax paper, because paper or wax paper is non-polar. So remember, the non-polar is formed by two atoms that are going to be equally charged, and so they're going to share those electrons. And so there's an electron going between both of them equally, and so there's no side that's getting the electrons more, so there's no negative side and there's no positive side, and so there's really no pull of anything. And so here the water is attracted to itself, but not the wax paper, because the wax paper has no pull, but the water does. Here we are with glass. We put some water on a slide, and we're just going to say for right now that the glass is negatively charged. And so the charge on the glass, as you can see, sort of pulled that water towards itself because it was attracted to it. And that is why we saw such a different reaction of water on glass and water on wax paper, because glass is charged and wax paper is nonpolar. And the same explanation goes for the water and oil station as well. Now we used some capillary tubes, and the properties present were adhesion and cohesion. So this is kind of hard to wrap your head around, but the thinner the tube, the more surface area is present. So the water can climb up. There's more surface per unit area for the water to be attracted to, so it's going to climb further up that capillary tube. And so you can see here that the water is attracted. You can see the adhesion here when the meniscus is formed. So the water is attracted to the glass, and so the water on the side of the glass climbs up a little bit more. And so whenever we read a graduated cylinder, we read right here at the bottom. And so the thinner the tube, the higher the water will climb. And so you should have created a little graph demonstrating that. So we also observed water and salt and oil and salt. And what you should have observed is that no matter how much you stirred, the oil did not dissolve the salt. So water is a universal solvent. We know that because water is polar, and it's going to interact with the positive and negative charges of the salts or of any crystallized structure, or many crystallized structures, or ionically bonded structures, I should say. And it dissociates. The Na and the Cl dissociates or dissolves, and that's why the water could break down the salt or dissolve the salt. However, the oil doesn't have that positive-negative side because it's nonpolar. It doesn't have a charge, and so it just sort of hangs out with the salt, not breaking it down, not dissociating it. And I think that was it. All right, I hope this helps, and your homework is to discuss 2 questions. It can be found on PowerSchool. Let me know if you have any questions. Be sure to use lots of key vocabulary terms and make sure you understand it very well. All right, have a great day.